So let's say I give you a difficult problem like this on the exam. How would you handle it? So let's describe this. Here we have a mixture of rotational and linear approaches to a problem that I hope you guys are able to combine together and figure out how to work with together. So here's the problem. We've got a wheel like this. It's a wheel that's spoked and it has a rim, and draped over the wheel is a cord, and that cord goes down like this to a mass, and that mass is held above the ground by some distance h, and we want to find out the time it takes for this thing to fall. Okay, so let's see if we can set this thing up. It's a complicated problem. There's lots of steps to it, and I'll try to work you through it bit by bit. So first of all, I would say develop a general plan. So the general plan is what you want to do is apply Newton's laws, like F equals ma, to this block down here, and you want to apply torque equals I alpha to this rim up here. So you're going to apply those guys. Then you're going to try to get some sort of equation, two equations, and then what you want to get is some sort of handle on the acceleration. So once we calculate the acceleration with two equations, we eliminate one variable and we get some sort of acceleration. And then from there, you want to go into the kinematic equation. Kinematic equations. And then from there, you can get things like, distance fallen, you have acceleration, you got time, you get initial velocity, you get final velocity, that sort of stuff. So this business here that I'm laying out, this is a rough plan for how to approach this. You're going to need torque equations to get a handle on the wheel. You're going to need F equals ma to get a handle on the block. And from that, you're going to get it down to kinematics. And then you should be able to answer this thing of the time. Okay? So let's begin. So let's deal with the easiest thing first. And let's just say this is the block. So here's a little block like this. And we're told that it has a mass of little m. So we want to do a force diagram on it. So something's pulling up, that's the tension in this cord, and what's pulling down is mg. And our standard equation is the sum of the forces equals mass times the acceleration that this block will experience. I'm going to take going downward to be positive, okay? So I'm going to say plus mg minus the force of tension equals the mass times the acceleration. That's a valid equation for this block. So far, so good. Okay? Now let's go into the rim. So the rim looks like this, and I'll just simplify it here for this diagram. And what we have is that this thing is going to be pulled on by the tension. All right, so this is sort of a perspective view. A side view of it would be something like this. The tension is pulling it down, and this thing has a radius of r. Okay, this is going to produce a torque. So the torque, in this case, is going to equal the tension of the cord times the radius of the wheel. So that's our torque. And we want to use this equation. The sum of the torques equals I times alpha. All right, so I can begin to put some things in here. So the tension times the radius, that's the torque. That's going to equal the moment of inertia of the wheel. So because this is a rim, we could look up on our table and find out that the moment of inertia for a rim is just the mass of the rim times its r squared, because all of the mass is on the outside. Okay, and then I put here alpha. So this is my equation for this rim. So I've got these two equations. I've got one up here, and let me just sort of, go back to this. Let me underline this guy, so that guy, and then this guy. I want to combine these two equations in some way and simplify so I can get to the acceleration. So let me write these guys down here. Let's go back to black. So I've got plus mg minus tension equals the mass, the little mass, times the acceleration it experiences. And then here, I've got r, tension r, equals capital M, r squared, times alpha. Now, this is the standard disagreement problem that we have. We've got A in one equation, and we've got alpha in another. And I'm going to have to translate between those two things. And what we know is that linear acceleration is equal to angular acceleration times r. Okay? So what I could do is I could basically say A divided by r is going to equal alpha. And now I can perform that substitution right in here. And if I do that, then I'm going to have tension times r equals capital M, that's the mass of the hoop, times its radius squared times a over r, like that. Now I can grind this equation down a little bit more and simplify. If I divide both sides by r, what I'm going to get is tension equals mr squared a over r squared. The r squareds nicely cancel, and then we get something like this. The tension just basically equals the mass times the acceleration. So this is going to help us a lot. I can now take this and substitute it into the previous equation. So I had plus mg minus t equals ma. That's just this equation up here. I'm putting it down here now. And now, instead of tension, I'm going to substitute in ma like that. So let's proceed with this. Plus mg minus capital Ma equals little ma. And what I'm going for is the acceleration, as I said. So I'm going to bring this to the other side, and I get mg equals capital Ma. I added that, plus little ma, like that. I can factor acceleration out, capital M plus little m, like that. That equals mg. And then I can basically get this. If I want to solve for the acceleration itself, I get g equals m over capital M plus little m. That's all equal to a. So that's now the acceleration of this little block as it goes down. So the block is falling with this acceleration as it goes down to the ground, like that. So if we go back to where we were, let's just take a look at the steps. We set this up, we got two equations, and we basically solve for the acceleration. Now that we've got the acceleration, we're going to do the kinematics on that. Okay, so let's do that, kinematics. So what we're asking for in this problem is we want to know the time it takes to fall, but we're given the height. Okay, so we want to know the time it takes to fall. So what do we know and what do we not know? So here are the knowns, here are the unknowns. So the unknowns, we don't know the time it takes to fall. That's what the question is asking for. What we do know is we now have a formula for A. We know the distance it falls. We know its initial velocity. That's going to equal 0. We also know about G. We know what that is. That's going to play into our formula here. We know capital M. We assume that's a given, and little m. So that's the mass of the hoop and the mass of the block, respectively. So we can take a look at our types of equations that we have. Let me just write them down for your convenience here. So velocity equals v naught plus at, or delta x equals v naught t plus 1/2 at squared. And then we've got v squared equals v naught squared plus 2a delta x. What we're looking for is time, okay? So that tells us this equation, it doesn't seem like it's going to work because it doesn't have time in it. So it could be one of these two equations here. And let's see, do we have enough? We have distance. We've got some sort of distance value. Distance doesn't figure in this equation here, but distance does figure in this equation. Okay, so let's take a look at that equation a little bit more in detail. Delta x equals v naught t plus 1/2 at squared. So the initial velocity is 0. So this thing is released from rest, so that goes to 0. And delta x is actually just the height from which we drop it. So the height is going to equal 1/2 the acceleration times t squared, like that. And if I want to solve for t, then I'm going to get 2 times h. So I multiply both sides by 2, like that. And then I divide by a, and that's going to equal t squared. And so t has got to equal the square root of 2h times a. Okay, so far so good. I know h. I can calculate a, but I'm going to put in a in terms of a formula. All right, so I got a there. Remember, a is given by this equation that we found out earlier. So I'm going to throw that in, and let's do this. I have this. I've got 2h. And now, if I divide by a, it's the same thing as multiplying by the reciprocal of this guy here. Okay? So that means I'm going to have gm at the bottom, and on top I'm going to have capital M plus little m, like that. That all equals t. So that's the formula. We put it all together. Once we properly insert a into this thing here, this is going to give us the time it takes for that thing to fall. Given the fact that we have a rim and not a solid disk, and that's going to oppose being rotated because it's got a moment of inertia. And that means that this thing will not fall as fast as if it were just cut. If I just cut the line here and it fell straight down, that would be falling at g, but it's not going to fall at g. It's going to fall at this other velocity, or this other acceleration like this. So hopefully that was helpful. It's a complicated problem, lots and lots of steps to it. And let me know if there's something you didn't understand, or if you have some hints for how you want me to improve these videos in the future. Thanks for listening. Bye.